the content in this slide, actually we will discuss about some recap about what you have learned before, which is related to the linear regression and logistic regression, and also some information that you need to know in order for you to prepare yourself before we go more technical thing, to talk more technical thing in artificial neural network as well as the deep learning part. Okay, so far this is just a common linear regression that you already know. So this is how you write the formula, and if you remember, if the linear regressions is a one-dimensional features, then you can just write something like this, which is y is equal to beta naught plus beta 1 x1. So again, this can be related can be related with what you have learned before in your pre-university syllabus or your A levels, okay, in mathematics in A level, where y is equal to mx, y equals c plus mx, okay, or mx plus c. So in other words, in this linear regression, now we just change the notation, so you don't get confused with that, because actually this is what things that you need to know, okay, why you learned before, why you learn about how to plot the linear equations y equal to mx plus c in your pre-university or A levels, is because that is actually the basic for you to learn about the linear regression, and then later you will find out actually the linear and logistic regression is the basic or the fundamental thing inside the artificial neural network. So again, the just change the notation, but it's still a near linear equation, okay. So means that this y-intercept here is represented by this beta naught, and then this m, which is slope, is represented by your beta 1. Of course, that is for one-dimensional or one variables input. So if you talk about the multiple inputs or more than one-dimensional input, then you can extend it into, you can generalize that equation you can express in this way, okay. So meaning that the d here is a number of features or number of variables that you have as the inputs, okay. So again, this is what we have learned before. This is what have been exposed to you in the previous lectures, and what I want to highlight in this video lectures is that actually this expression can be represented by many with several type of representation, okay. One of it is from this equation you can simplify by having this kind of, you are using a summation here, okay. Of course, if you want to write this thing, it might be too long, so that's why you can simplify by having equal to fx here is equal to your beta naught plus the summation of your index j, bj multiply bxj, where this is the one that from 1 to the d, which is the d is the same d here, as here d represent the dimension of your features, okay. Other than that, you can also represent your linear regression or linear equation using another representation, which is called matrix or vector. So as you can see here, the same equation here, you can also, okay, this is the same equation as before, and then here you can see that now it should be the same thing, okay. The j here is the index of number of dimension, number of feature dimension, and then the I over here is a number of samples, okay. Meaning that if you have x1 and x2, then your d is equal to 2, okay. But number of samples should be, maybe you have a data set of 1000, then your I can be vary from 1 to 1000, so that is I. So from here you can see that again, instead of you can having this kind of representation, you can also have this kind of representation, where this is always you see in scientific research paper, they always write the equation or all the linear equation, all the algebra using this representation, where they always do some bold there. Okay, so that's why if you see any notation in scientific paper, if you see there's a bold there, that's mean that's a vector. Okay, some use small letter. Okay, some use small letter like this one. Okay, small letter can be represented by vector, and if you talk about capital letter like this, it actually represent the matrix or a set of two-dimensional vector. Okay, each one-dimensional vector, it's always represented by just a small capital, but still a small letter, but it's bold. Okay, so again, let me delete all these things. Sorry. Okay, so that's how you can write. Okay, you can see that why we can't have this kind of things. If you see that, that is because if you arrange this one, okay, because again this bold beta is actually represent a one-dimensional vector or matrix, which is your B naught, B1 until BD. Okay, so then your x here, okay, your x here is represented by, you know, your sample of which is your represent your x, it should be xi, sorry, it should be 1, and then you will have xi 1, then xi 2 until xin, which is your number of samples. So in other words, if you talk about the multiplication between this one and this one, which is actually represent this equation, okay, this one, again, this is how it should look like. But when you extend it into, you know, let's discuss about this expression. Okay, this expression actually you can have, you know, if you have some matrix like this, beta naught, beta 1, beta 2 until beta n, beta d, and then you have another one, 1, x1, x2 until xd. Okay, so if we want to have, okay, if you want to change this equation into a matrix form like this, okay, it consists of two components. One is a set of beta, another one is a set of your x. Okay, then one way you can do is that, let's say this is your beta, okay, it's a bold beta, and you assume this is your, this one, okay, this one is equal to your bold x, okay, bold x. So in other words, then you can, you know, you can represent in this way. Okay, y is equal to, sorry, so y is equal to fx equal to your beta transpose x. Okay, why transpose here is because once you transpose and then you multiply with your x, then actually that will become element wise multiplication. Okay, it's a dot product there, it should be dot operation, dot product operation. So means that that's why in this equation, okay, we have this kind of thing, which is the transpose, meaning that now you have that matrix, and then that matrix has been transposed, then you have another matrix x, then you multiply element wise multiplication, which is represent the dot product. So that's why that can also, this thing is also can be represent your regression function. Okay, it can be represented in this way, it can represent in this way, and again the one that you learned before is this one. which is the one that is the most easy way to understand. Of course, this one is the most easy to understand, but when you see the technical papers or scientific papers, it always written in this form. Okay, so again, this one can be extend in this way. Okay, it means that let's your y here equal, this is actually your data set. Okay, this is the output value, and this is the input value x. Of course, your x, you have let's say 1000 going into this way. Assume that you have 1000 samples, so this one going into 1000s, for example, and x also similar. In this way, it going to 1000, but in this way, it's going into your number of dimension. If your number of dimension, let's say you have 3 inputs, then your d is equal to 3, for examples. So that is the whole data set there. Okay, the input is represented by this vector x, and then that is why you can see here they use the capital X, because if you talk about the matrix or two-dimensional vector, they always use a capital X, a bold capital X. Okay, why if you are using one-dimensional or one-dimensional matrix or one-dimensional vector, they always use a small letter but it's bold. Okay, that is how the standard way how the mathematician do some notification to the equation. And again, if you, this one is, we talk about your parameter. Okay, there's a lot of term they used to call this one. Okay, you can call it parameter because previously when you talk about the hyperparameter tuning, okay, you can also consider this is as a hyperparameter. Okay, and of course, if you talk about the typical mathematic, the fundamental or the one that you learned in school before, they also represent this b naught as your y-intercept and b1 is your m. Okay, which is slope. Of course, that is for one-dimensional input. If you talk about the multiple dimensional input, then you have a lot of, just considered as a lot of slope. Okay, you have m1, m2 until the d there. Okay, it wrap up all together in one set of beta. Okay, then don't get confused, because sometimes if you see some node, they are not using beta, they are using a theta. Okay, theta 0, theta 1, theta 2. Okay, then you have a theta bolts there. So some people, in some book, they are using the theta as to represent your hyperparameters. Okay, the parameter that you want to tune later, which is that is the one that you want to tune later to get the optimized equation or linear equation that can fit with your given data. Okay, so in other words, from here you can see that, okay, you can also in general you can write this equation in this way. Okay, meaning that to predict your y hit, then you need to have a function of the capital X bulls there, which is this one, and then this one can be represented by capital bull X and beta bulls there, which is this one is this one. So you can see that from here you can summarize that this is how we represent the linear regression, and later we talk about logistic regression. It's also similar. Okay, logistic regression is just added another equation which will be cascade with this linear equation in order to change the regression behavior into classification behavior. So that's how it's work. But this one, the one that I would like to stress here is how we can represent the linear regression in matrix and vector. Okay, if you can see the one that you learned before, the one that can be considered the most understandable is this expression. Okay, the one that you learned before. But because why I highlight on how to there's a many how I want to highlight actually. There's a lot of way to represent this linear regression, because later you need to familiar with this notation, because most of the things that we learned in especially artificial neural network, involve equation that represent by vectors. Okay, so that's why I always stress on that, so later we not confused. It can be this way, which is represent by the summation equation there, summation symbols there, or you can it also can represent in this way. So that's why I hope you need to familiar with this representation, because later there's a lot of notation that represent in this way, or there's a lot of expression that represent in this way.